today we're going to hear from Gaines Cardosi over here, and he's going to talk to us about from developer to data science. So Gaines is an associate director at UBS. He's an organizer of Music City Code, which is coming up in June, by the way. He is a Microsoft MVP, and he's a board member of our meetup as well. So without further ado, Sonia.
So this is the world of big data. It's all the different tools, well, obviously not all of them, but all the major tools, platforms, frameworks, languages, plugins that are common in this world. And this was the impetus for putting this talk together. It's because I started looking into data science. I see the direction things are going in. This is something I want to do. But then the more I looked at it, the more questions I had. And I'd spend a couple hours researching, and then by the time I finished, I felt like the things that I didn't know were stacking up quicker than the things I did. So let's start with big data. The first cornerstone that we'll talk about for classifying data as big data is volume. That's pretty easy to explain, right? Lots of records, lots of tables, files. So the reason why this is cornerstone is because the amount of data we're generating and capturing is skyrocketing. I don't want to use the term exponential because that means something very specific, but it's taken off. In fact, we're supposed to have 2.5 quintillion bytes, that's 2.3 trillion gigabytes of data created each day now. And that's 40 zettabytes of data. That's 43 trillion gigabytes by 2020. It's incomprehensible. And the majority of US companies already have over 100 terabytes of data stored. This is a common asset that's being underutilized for many companies. So, volume's easy to understand. Let's talk about variety. There's a couple key components to understand. You're probably familiar with unstructured data. You know, if you work with SQL or Access, if you looked at tabular data, that's structured data. Unstructured data is, I mean, you're familiar with these concepts. It's images, it's books, it's music, it's things that they're not tabular, they're not broken out into like a class hierarchy for you, but there's valuable information there. So approximately 80% of what enterprises have in their data storage is unstructured data. So again, those are assets that you need some sort of tooling or skills to utilize. An example of this would be 30 billion pieces of content are shared on Facebook every month. So you can imagine the kind of value that they put out there for the taking. So the third point of big data is velocity. Notice I don't think I said component, because I don't want to imply that all these have to be there. These are all facets of big data. So for velocity, we're talking about the speed the data comes at you. For instance, Twitter, it's a constant stream of data, right? We're not worried about archiving every tweet that ever happened, personally at least. But we want to be able to process them in real time, maybe to be able to react to them. We'll talk about some of the implementations of that. So let's talk a little bit about data science. To me, it's a very logical definition, right? We have some data we're working with, and we use a hypothesis with a scientific method to work with it. But it gets a little bit more complicated than that when you start talking about what goes into it. One component that I assume almost everybody here already has to some extent is what I'm coining as hacking expertise. You might also see this talk like a programming ability, or the general idea here is that you've got some sort of technical skills you can leverage, the ability to work with data, to write functions, and you got a little bit of creativity on problem solving. So when you add in statistics, some understanding of basic math and statistics to that, which is the ability to understand how you go about solving that problem from a functional perspective. I'm not talking about functional programming, I'm just saying the sort of functionality. The intersection of those two is machine learning. So that's where you can set up a system, you can give it some parameters, and you understand how to write the correlations, and let the machine figure out how these connect. A good example of that would actually be the Connect for the Xbox. There wasn't enough room in the Connect to put all the programming that we need to be able to identify every person that stood in front of it and all the positions they'd be in. So you know how you calibrate it when you first set up the Connect? you're teaching it. You're giving that machine learning some information so that it can then teach itself the proper algorithms to work. So the third aspect, or third skill set, is domain expertise, or subject matter expertise. This is understanding the data you're working with and the kind of problems you're approaching. So in the intersection of these two, of statistics and subject matter, we've got traditional research, right? You're not having to write any programming, or not much at least. It's more about working with the math and the domain and figuring things out. But where the hacking expertise overlaps with subject matter, that's where most of us live, is writing software. You might notice online they put the danger zone here, which I think is funny, because when you think about it, like when I think about it, programming, when you intersect that with domain expertise, you get consulting, you get writing applications for the organization, which it might be the danger zone, depending on where you work, how you go about it. But the idea being, if you have all three of these components, where all three of them overlap, that's data science. Now, that might be a little overly simplistic, because we really need to add in some social sciences too. If we don't understand how people behave, then we can't necessarily understand the data we're getting or how we need to utilize it. A good example of this would be self-driving vehicles. If you don't understand how people might be driving on the roads, if you're just going to assume that everything's going to behave like that self-driving vehicle, it's not going to be a very successful vehicle. You also have to consider how the results you bring out are going to affect the people, what sort of conclusions are going to be drawn. And then we've got some little, if you like the little intersections, the idea of holistic software and holistic research is saying you understand how this is, what the behavior of the users are, the user experience, how it interacts with them. So how do these overlap? The concept of big data and data science, because they're not the same thing. Right? We define them very differently. So I saw somebody online who coined this phrase of the overlap, big data science, which actually seems to be a pretty good fit. Because when you think about it, I put the little triangle in the corner for reference. If you want to do data science, but you have data that's it's only volume, right? There's no velocity, there's no variety, it's just a lot of data. That's not big data, really. That's just a lot of data. We do that sort of stuff all the time. Genetics data would be a good example. So it's very defined, the structure of that data, but you're going to have a lot of it to work with. So predictive analysis would be a great example here, where you teach the machine how to draw correlations between the data and a state, and then predict that state in the future. From the same perspective, if you have data that has high velocity, like those Twitter feeds we were talking about, but no volume or variety, it may be like the streaming earthquake information where you want to do a rapid alert system. All you care about is the data that's coming through at the moment. You're not trying to deal with massive backlogs of data. You just want to know within the past several minutes what's been going on. If you have only variety, that could be like facial recognition. Anybody here use Lightroom? Or I guess even Facebook, that when you tag people on there, it gets facial recognition. There's not a whole lot of pictures in your library. There might not be a whole lot of pictures that person has been tagged in, but there's a lot of data in those photos, a lot of variety there. And then you got combinations of the two. So volume plus velocity, well, that's a lot of data, and a lot of data coming quickly. You might be working with jet engines that have sensors on them. So you need to process that data quickly to identify any errors. You also need to store that data and process it later to do diagnostics. Velocity and variety might be taking that facial recognition system and doing it on surveillance video. So now you're live streaming this video and processing it in real time. So let's talk about why this is even important. Right? What's the big deal about data science? The prediction is that there's going to be humongous growth. We're already seeing it. The prediction was by this year, have 140,000 jobs that could be met. Google's chief economist said that the statistician part, this being able to work with statistics, is going to be the sexiest job in the next 10 years. It's already one of the top paying jobs. In fact, I read some numbers about 6 months ago, and I came up with about $160,000 median salary for data scientists, compared to 118 median for software engineers. Obviously, this isn't all adjusted for cost of living, but you can see that a 40% increase in salary is not going to see that. So what does the job entail? I like taking a holistic view. I've been doing consulting most of my career, and the first thing you got to figure out is the business addressing the problems that need to be addressed. And generally, in my experience, they need you to tell them what needs to be done. So being able to understand the business, understand the assets you have, suggest what problems you might be able to address with those assets, form that hypothesis, that scientific part of the data science. And then we'll get into the actual process of munging data and working with it. But that's actually that's the behind the scenes part, right? The part that the business is impressed with is, can you identify the issues, can you quantify them, and then can you convey whatever results you have. Maybe they were not meaningful, but at least that in and of itself is an answer. It's something that you need to be able to convey. So the first step is getting your data. We'll assume for this example that you've got a data set. There's a bigdata.gov is a great source for free data sets if you want to take around them. So the first thing you want to do is figure out what you have. That's where the sampling comes from. You want to make sure you sample across your different categories or how your data is broken out. Your data is probably not going to be complete. A lot of the big data sets these days are missing some important values. So you have a couple ways of addressing that. Either you can say, well, any records that don't meet certain criteria for having complete data, we can just throw them out. Or you can infer it. You can guess. You can say, based on the averages that I've seen, we'll just substitute this number in. Of course, sometimes numbers aren't very useful. You want to be able to get a relative relationship between records. So you can normalize the records, especially if they're coming from different data sets. Maybe you've got temperature readings, and the temperature readings weren't calibrated quite the same. There might be some normalization. The derivative values is actually pretty cool. The idea that you could take, let's say you've got a range of 1 to 1,000 on some value, but that's not really meaningful. You don't care what the specific number is. You just want to know what the relationship is to what it should be. So you might want to put those in the categories instead, and then run your analysis on the categories. And then keep in mind, for a lot of purposes, you actually need a set that you're teaching the machine what it should be looking for. So that's a training data set. So you're going to need to pull some of that out. So you have some of your data to test against or to teach it. Let's talk a little bit about the tooling to do this. I pulled a lot of statistics down, and not all of them are from this year, and not all of them are from corporate America. These in particular are from 2015. And they relate to scholarly articles, which is research, usually at universities. So the tools they use in those tend to be a little different. You'll notice MATLAB is pretty high up there. How many people here use MATLAB? More than I thought. Well, according to this, it's the 5th most popular tool. That's more because this is coming from papers. So they're looking through papers that have to do with data science and looking for keywords. But you do get a sense for what's most common in that field. There's going to be some crossover as we pull more people from the education field into corporate America. What I'm more interested in than knowing what's currently being used, because the education sector tends to lag a little bit behind, is what are the trends. One of those Python and R are shooting up. I was actually really surprised that this said Hadoop was declining, but if you notice on the graph, it's not declining that much. So I don't know if I would buy that specifically. Plus, well, this might be a good time to get into Hadoop. I put that in there for a reason. Hadoop's just one of the many platforms you can use. It's not just a single tool, it's a suite of tools. The reason I mention it is because it's very highly used. And there's, I think, about 150 different projects for plugins and components for Hadoop. So I wanted to touch on a few of those, just so you're familiar with them. The platform that Hadoop's built on is the file system, HDFS, and that allows it to distribute that data across machines. So that's really the key to how Hadoop is able to scale like it does. And you probably heard the term MapReduce. That's the traditional approach with Hadoop is mapping this function against this data in a way that it can distribute that to a cluster of machines and then reduce that to something meaningful. Now there's a new approach called YARN, which I think people are applying MapReduce to in R2. That stands for yet another resource negotiator. But whereas MapReduce is built to be batched, YARN can do streaming or even graph processing, which is like crawling your social media tree, for instance. So there's a plugin or a component called Pig, which is Pig Latin programming language, and it's used for writing those MapReduce programs. There's something called Hive, which is summarizes queries and analyzes data. HiveQL is the language. HBase is a NoSQL database that works with Hadoop. Storm enables stream processing, so you've got that IoT device that's just throwing data at you, and you need to take that fire hose and break it down to something more meaningful, usable. Spark is a fairly new component in the last couple of years that allows for in-memory processing, which can make your analysis go a lot quicker. And these are just a few, just to throw out some names so that when you look at that chart and you start seeing things online, you have an idea. This is actually, it's used by Yahoo, it was created by Yahoo. You'll notice it's called Apache Hadoop, that's because it was made open source. And it's used by LinkedIn and Facebook as well, to give you an idea. This is pretty mainstream. One of the big questions that comes up is what language should I program in? Right? What language should I be writing my MapReduce functionality in? Python and R are the two most common languages seems to be used in the data science community, and they're both increasing in usage. The R tends to lean more towards the scientific side. It's a statistical language by its nature. It actually came from a language called S, which stood for statistics. Whereas Python was made in 91 to be more of a faster production, more readable language, general purpose. So you'll see that a lot more in the developer community. Anybody here a Python developer? Excellent.
Balls.